שלום. לא פגשנו מזמן, לא ראיתי. иди сюда, иди сюда, иди сюда. Попробуй
Не надо первое.
Послушай, Агата, вот здесь что-то стоит, что ли?
Да, здесь портфель стоит.
Это мой портфель, я его просто отложу в сторону.
Здесь, да?
Да.
Хорошо.
Так, здесь открыто. Чудесно. Я сейчас принесу ему кофе, и это займет несколько минут. Вы не смущайтесь.
Вот.
А где Даша?
Даша там.
Женя
вместе
показывает,
сидит.
где она, нет?
Нет, Даша там сзади сидит.
Я сзади, мне казалось, что я спереди.
Ну, по сравнению, не знаю.
So we continue the second course that treats the angular groups. So let me now let me treat as the general rank case of the canonical form of a word. So then we will discuss the following situation. Given a linear word, we first assume that it is canonical in rank k minus 1. Now we describe the number of steps until we reach the canonical in rank k. Let me recall that we have divided all the relators in the groups R1, R2, etc., Rk, minus 1, Rk, and so on. And actually, we assume that all these relators are canonical in rank k minus 1. Now, how do we define the canonical in rank k? First of all, we consider the chart in rank k. What does it mean? We take the angle relators in the way we have discussed them in of rank k, and we consider all the occurrences, maximal occurrences of relators inside this word. It means that this is a part of the relator, and if we take even one more letter in one side or another side, this already will not be a part of the relator. In this sense, it is maximal. Now, and let me also recall that we have defined an L measure on the relators. Let me recall how we have defined it. Every relator is a form set A, B, n times. Then it is, we assume that it is a reduce it as written, so we only take the measure of the A vortex. We just omit the measure of the B vortex inside. Now we look on our constants. We have constants from 0 to 1, half, alpha 0, alpha 1, alpha 2, and alpha 3 are some fixed constants. So first we can assume that our word is alpha 1 semi-canonical. Alpha 1 semi-canonical. It means that in no place that all the measure of all occurrence is less or equal than alpha 0. And it is also easy to see that every word, every element has a representative, that it is canonical in rank k minus 1 and alpha 0 semi-canonical. Now, the next point is that we consider the one layer map defined by all the number 1. If it's number 0, semi-canonical words representing a certain element.
Even alpha 0.
Alpha 0. Only before
And-
lambda.
No, of course, these are called lambda, I apologize. And also, of course, here we need to say lambda 0, thank you. We call all the constants lambda, doesn't it? So, what will this mean? It means the following, that we have different words, all of them were assumed to be canonical in rank k minus 1, and representing the same element. Now, it is important to stress that actually a part of what we had in the case of small cancellation groups or of birdseye groups, here it could be that for the same word we may have the number of words representing the same element could be also infinite. Actually, it means that they will differ by a choice of a parameter, because we know that our relators depend on two integer parameters, as say a to the power alpha, b to the power alpha on one side, b to the power beta on the other side, and what I call 2t to be all these relations. Now, and then this, of course, alpha and beta may run through different integer parameters.
What is T? What is T?
T, when we write the T2 is T2 of AB. This is a part of how we define the structure of an angle word. We have B to the some power. This was the second B to the power beta. No, we call this word T2 of A and B, and here T2 of A and B, also here T2 of A and B, T2 of A and B. Then we had the current relation T2 of AB is equal to T3 of AB times B times T3 of AB, etc., etc. This was the series of recurrent relations that defined the angle relator. So actually these are long words. Unlike here, B is a short word with respect to this, it doesn't matter because alpha and beta may be very big. In any case,
So, sorry, A and B,
are fixed words.
which is bigger, which is one, which is small, it's not.
No, when we define it Rk, so we assume it that A is a certain range of lengths. Particularly, it was to say the length of one was bigger than 2 to the power k minus 1 times 10 plus 1, 2 to the power k times 10, and that actually we assumed also that A is, say, bigger than 16 B if you need. So this is also the result of generality. Yes, some constants you can manipulate if you wish, but this is the layer number k of the relators here, and A and B are the generators of the angle relator. In any case, what happens here is that when we consider the power of B, so we may have different words in the one layer map, but if we just look on B in a certain power as just a parameter, then we will actually have this a kind of a single possibility for this. So, and then we actually have a one layer map almost in the usual sense, but subject to the conditions that these cells might have in some places the integer parameters of alpha and beta, and this will relate, and this will give actually an infinite number of passes in this layer map, depending on the choice of the integer parameters. While formally we write it as a finite one layer map, but subject to this remark about the integer parameters. In any case, when we have this one layer map, so we proceed further to define the certified one layer map. Certified one layer map is will be sub map of this that consists of these edges we are able to certify. What means the certification? That we are able to find the paths inside this map such that satisfies certain kind of inequalities on its chart. Because when we have this path, it also has its chart. And then we know the lengths of each of the occurrences in the chart, and then they are numbered to a certain particular restrictions, which we not repeat now because we have discussed. Some more details should be added there, but it doesn't matter here. A witness is a path subject to certain conditions on it. So, and then if a edge is certified, then it belongs to the certified map. If it is not certified, so we just omit it from the certified map. Now, and let me also recall that we have stipulated this restriction in a way to be able to define what we call the dominant areas in a certain way, so that when we actually form the triangle of canonical words, it has special properties which we will need further. In any case, the second step is to take the certified one layer map. Now, the next step is to let me also stress that certification is a global procedure. It depends on the existence of a witness that goes throughout the whole path. So if we change on the end, so the result might be different, but it could be different under very specific circumstances. Now, then we take the next, taking the locally best edges, locally best edges. It means that if we have already this certified map and we would like to determine what size to take, then we have to go and excuse all this assume already belong to the certified path. So we look one on one side, one on the other side, and then we check all the possibilities to go one way or other way. Let me stress that while I'm taking these alternatives, I have then to take the canonical for one, because when I say I take the complement, it doesn't mean in the simple-minded way. Let me say I just have to go on each of the sides and then to take the word canonically in rank k plus minus 1 for this pass. So just it is not just an alternative because, but then in any of these places we observe what is called canonical triangles in rank k minus 1. So we assume that their behavior is as assumed by the inductive assumptions. Now, in any case, so what we have after all a certain occurrence in the K chart. Whether we take this way or we have 16 possibilities to look on it, 8 on each side and direction, and then we compare them using the short lex comparison. And if one is a winner, this is the side that wins in this local competition. However, in the case of hyperbolic groups or Bernstein or small cancellation groups of Bernstein groups of the odd exponent, then there was only one winner in this competition. But if this is exactly the reason why we cannot proceed in this way for Bernstein groups of even exponent, because we might have exactly two winners. This one and this one, u and u are exactly the same. The whole relation is the square of u, and then it may happen that they are both equal. So we cannot change. We cannot choose a winner in this, unlike the case of the odd exponent. Here we also might encounter the situation that we have just the full symmetry, so they are absolutely equal. Now this is in fact actually a very important point in this, because now we have to decide where is the situation when we have this symmetric situation. And the answer is precisely this way that we have here. When we look on this way and on this way, so they are precisely symmetric. It is important combinatorial fact. This is the only way that they might be in such symmetric way. Of course, I mean, it also here could be that this one and this one are exactly symmetric. So one of two situations may occur. So, which it means that this next step that does not give us necessarily one path in this to the side, but here might actually be the situation when we have exactly two things will be the same in many places, we don't know here, but this is the actual possibility when we look on these edges.
Only two possibilities? What about the integer parameter? It doesn't.
Oh, this is precisely my point. Is what happens here that assumes that on one side we have this lower side, the upper side, and the integer parameter will be precisely the mean. This will another way. This what actually happens in a symmetric way.
No, okay, but you said there are only two possibilities.
I mean horizontal or vertical.
What?
And then of course it could be to a certain place symmetrical, it could be the ends.
No, but the integer parameter in the middle, there's only one possibility, or there could be several?
No, this will be my point now. That actually there will be a possibility to manipulate the value of the integer parameter in this.
Also, there are more than, there could be even infinitely many possibilities.
Of course, but when we just when we neglect the value of parameter, then we have a symmetric situation. But actually, it means that we have inserted here all the integer possibilities. What we
Yeah,
have.
but in the Burnside group of the even exponent, there's a phenomenon of dihedral group that actually exists.
Excuse me?
In the Burnside group, there is a dihedral subgroup.
Of course, this is the whole point there. That there are finite two groups which must appear.
But here, such phenomenon doesn't exist.
Not at all. No. The whole difficulty there was to classify the possible finite two groups that appear and to see how they intertwine with the diagrams. But here the situation is very different, but also we have here these possibilities of then what actually means that here how we encounter the flats, because if we take this and then we just can give this integer parameter a very big value, a very big power of b. And then what we need is exactly the same way it goes here, or it goes here. Actually, this could be crossed in any point in the middle. So let me just explain how it occurs. Just look on this as big powers of b, and then this way to cross it appears in any place. This one or this one, all of them are actually the same word. Yes, depending where we place it, because if we can change these parameters of b.
Yeah, but the next one, the neighbor of this, can take only part of this b.
Oh, here is precisely the point. So first we discover all the places where a flat is possible. Now, so let us mark them. Now, maybe one is nearby the other, completely possible. And the question is, what would be now? And etc. etc. So we mark on this way all the possible flats that we have that coming from occurrences in the chart in rank K. Now, then we have the following question. Maybe, so the simplest situation is that we have two nearby flats. That is exactly possible. And then they will give us a composite flat. Now, maybe this B and this is another B, so they do not match together at all. But the situation is following this is the same power of the same B, but what is this in between? In between, we may have the following situation. Let me return to the third word that we have looked on it when we consider the case of rank k minus 1. So, we had here, for example, some of these words. Now, here we had this flat and the other flat. Now, maybe that inside this word, here we had a B flat that may be consisting of many B flats of lower rank. I mean of rank less or equal than k minus 1. Here we have a flat of rank k, here of rank k. All of them have the same part, the same B. The same B, and then it might happen that this will fill in the gap between two flats in rank k.
But the height of the need will be the same.
Okay, now, this is the point. When we define the canonical form, that we require that all these flats should be crossed horizontally. This is a...
Why? But in the measure you don't take into account the D's.
What do you mean?
In the measure, you
Yes, of course.
don't take into account.
It doesn't matter. It does only mean that we had to choose some power, and then we go the some power through all of this.
What's the, this is an additional requirement?
No, now when we are going to define the canonical form, we stipulate that all the flats are crossed horizontally.
But these are, you can consider them as different flats, so...
No, actually the composite flat that is composed of many various flats, maybe of different ranks even.
Yes.
Now, but what we say, when we defined the canonical form in the previous rank, so we crossed this horizontally together. Now, why?
Why? It's not part of the definition.
No, I'm going to define the canonical form, and this is a part of how the canonical form will be defined. So we need, this is actually very essential, we need to cross all these flats horizontally. I mean the same place. Now, but we have to define at which place. So we...
So the definition is not local anymore.
So, excuse me?
Definition is not local anymore.
The definition, no, certainly not. After we have chosen this, discovered the flats.
You need to identify the flats and then define this thing.
So actually what we need, first we identify the flat. Second, we see maybe two flats are connected by a composite of flats of lower ranks, which we see by induction. So what finally appears that inside this word, we have a number of flats. I mean already of composite flats. Now, one possibility is it could be from one end to the other, but assume not. So here we have some band of flats. Here we have another band of flats, etc., etc. Now we have to define the connecting passes. How? Maybe this is a connecting pass here. Excuse me, a connecting pass, etc., etc. How do we define him? Because actually, this is a power of a certain B. This is the power of another B. So maybe this is B1, this is B2, B3, etc. This will be B2 both, this will be both B1, B3, etc. So what we do? We look on the this word. This may be just an arbitrary word, canonically 1k-1, and then we take an arbitrary big power of B1 in both directions, here also, and we compute the word. I mean the canonical word in rank k-1. So it might have a triangle here, or a triangle here, and this will be canonical rank, canonical word in these directions. And this for every path that is between two different composite flats which we identified. Now, what happens is the following. We have to say how we will cross this. So we have...
Just, before you define the one-layer map, right?
Before?
You define the one-layer map in step 2.
Yes.
So these are parts of the one layer, yes?
This, of course, when in this one layer map, this will be the symmetric part of it.
Yeah, but the path in between,
Oh yes, this we see exactly. This is actually we see in the step 4 when this is the one. This is when the decision procedure was unique and gave us a certain path. Because either we have a flat or we have a uniquely defined path from this procedure. Because we knew that some of them was better and we just take it locally in every place a better one and take...
But you don't have unique here. I mean, it can be in any level.
No. It is, this path is unique.
Why?
Because here is where the procedure in step 4 gave us a definite transfer. Because then we had two possibilities in the one layer map and one was better than the others. Whereas a flat, whereas not a symmetric situation when you do not have the unique answer. So what happened here? We are able to have two answers. We may go this way, or maybe there is another thing that goes so. We may cross it this way. So two possibilities. We go here, cross it, and then go to this place, or we go here. So we have two possibilities. Just because enter here and go horizontally, or enter on the other side, go horizontally, and then connect. And this is actually to have to choose in the group in the Z2. So what? Okay.
No, I still don't understand. I mean, if the why there will be only two possibilities, and why?
No, because we decide that when we have this composite flat.
No, okay, I understand that, but for these paths, you say that they're placed the path in between.
Oh, the path is
they are uniquely defined.
Actually, it is uniquely defined up to a canonical triangle.
Why can't you raise the path, lower it down?
No.
Why?
Because I'm taking this. I'm adding here any power of B, positive or negative,
Yes.
and then the computation will leave me in a certain place. It doesn't matter how many B's I know, because here, assume that this...
You don't count the B's, it's not part of the measure.
No, but no. I just compute the word. Because I take a big power of B, a particular word, and a big power of B, positive or negative on both sides.
Yes.
So then let me just make this B indefinite, and compute the canonical form. If I add powers of B, it will not change the spaces. So this is how it is established. Okay. This is a simple point. We just take here a power of B, indefinitely big, this word in between, this is a power of B1, here an indefinite power of B2, and then we compute it, and the computation should give us a definite result, independent of the number of this, and this will be our result here when we take the canonical form of rank K minus 1.
What confused me is that you don't consider the B only when you consider higher rank, higher class relations, yes. Because the B is considered as it does take part. It's part of the measure when you go down.
No, only when we establish which side to take, then this word doesn't play a role. But otherwise, it is a virtual word containing the A part and the B part. We just take this way to compute this path in between. It is uniquely defined up to the question whether to go to the up or down on both sides. So there are 4 variants, which is differ by canonical triangle of rank K minus 1. Now, and this is the situation in all places we have these flats. And then when we can go one way, and then we cross horizontally, then go to the connecting path, go horizontally, or we could do the other way. We can go here horizontally. So actually we have only binary choice in crossing every flat to start from this point and end over this. And then we can decide using the canonical form in words of Z2. I mean, we know if this is a positive power of B, then we first go here and then cross. If it is negative, then we first cross and go here. And then this word will be, this choice will be equivariant up to taking the inverse operation. Because if we inverse the word, so,
if you inverse, you don't get the same?
If it will be the inverse, so the inverse, or the canonical form of the inverse word will be the inverse of canonical word. I mean, this can be equivariant.
So can you repeat what's your doubt?
No, I didn't understand why the path in between the flats are...
How we determine it?
Yes.
So first, it was defined in some way when we have taken this part of the one-layer map, which have a clear decision between the sides.
And we made decisions not on L measure, but actually on precise lexicographical comparison,
yes,
right?
Because
so
the short lex,
yes.
Okay. After all this is a short lex decision. So one of these should be preferable.
That's why it doesn't matter that we do not use B in L measure.
Yes, in any case, I feel if actually with or without B is a result, no, better with B, of course, with B. In the short lex, we actually
Yes, just precise short lex comparison.
Yes. Now, so, but then we have a certain path. But we have actually, we carry to, again, to return the word that should be itself canonical rank K minus 1, because we have here the word, so we can, its own canonical form in the rank K minus 1, but here have a power of B, which is a canonical word in previous ranks, and then we have to compute a big positive or negative power in B, then this intermediate word, and also a big power of positive or negative of B2 minus 1. And then we just, it may cancel to a certain place, it may give us a canonical triangle. After all, we are left with a certain word which does not depend on how big power we take B or both sides. So this is a definite procedure. And then we use these passes in order to define the crossing all the length on the left on the right as we decide actually to the power of b is positive or negative. So this gives us the canonical form of the word in rank k.
So the result
And
is,
when you consider these composite flats, you consider